Okay, it has been said that turbulence is the last great unopened problem of classical physics. And it certainly is, well, one of the last, let's put it like that. And it certainly is an old problem in the sense that the equations which are believed to govern it go back more than 150 years. So in that sense, it's maybe not such an outrageous prediction that maybe in the next Visions conference 100 years from now, it might still be discussed, who knows. Anyway, the problem of turbulence in a very few words is how come these equations, this simple partial differential equation, simple looking partial differential equation here, how come it have as its consequences the complicated motions you observe in waterfalls or tornadoes and so on. Now, what we have here is an equation for motion of a fluid. So fluid here means you can think about air or water or liquids or gases of that type. And we describe that motion by a vector field. So we are in RD. D physically is 3 or 2. So we have a vector field in some region, which sometimes I take bounded, sometimes unbounded for the mathematical study. And the vector field is time dependent, and that vector field has some dynamical equation, which is called the Navier-Stokes equation. And that equation is a very simple equation from conceptual point of view. It's just Newton's law written for the fluid element. So U means the velocity of the water at point x where you are sitting and observing it at time t. So you are just looking at the water going past, and you measure the velocity at that point at various times. And that satisfies this equation. And the equation is of the form acceleration, namely derivative of velocity with respect to time. Acceleration equals force. There is a term, this nonlinear term, which comes from the fact that you are sitting and watching the motion of the fluid instead of moving with the fluid element. So that's a natural thing which naturally occurs there. There are forces which the nearby fluid elements exert on the little one which we are looking at. That's called pressure. So the gradient of the pressure enters as a force. Then you have some external force. So you're mixing coffee in the coffee cup, and the external force is the motion of your spoon in the coffee cup. And finally, the only non-obvious term is the frictional force coming from the internal friction of the fluid from statistical mechanics, eventually irreversible processes taking place. And in Navier-Stokes equation, that frictional force is modeled by the Laplacian. And there is a coefficient which is called the viscosity. So that's the equation. And with a little additional condition, we are discussing incompressible fluid flow, which is very good approximation in many, many practical cases. All right, so viscosity, that's the friction. The pressure in the case of incompressible flow is actually a function of the velocity, so it's not an independent term. So that's the partial differential equation. And before, well, what I want to do, I want to explain you, try to convey at least how the problem of turbulence could be posed mathematically, and then tell you a little bit about recent, during the past 5 years, understanding of similar problems, not in this equation, but in a related equation. All right. So to understand, we have to first understand what sort of situations we are after. So here are 3 pictures of experimental setups where you study turbulence in laboratories. This is supposed to be 2 concentric cylinders. I'm looking from up. The cylinder inside is stationary, it doesn't move, and the outer wall is rotating. So as a consequence, it's inducing a motion to the liquid in between.
Usually they do vice versa, they rotate in.
Yeah, very good. I put the arrow here and I didn't want to erase it anymore. anyway, whatever you do, in this system there is some characteristic length, namely the size of this system in this case. The size where you do nothing here and you do something, the distance L from that. There is another case of interest. Imagine a body, a ball or a cylinder. Let's put a ball, for instance, and you send. So it's sort of stationary in the space, and you send fluid with constant velocity to the direction of that ball. So something happens, then the fluid has to go around, and something happens on the right-hand side, depending on the velocity and on the size of the ball. And then there's maybe one more thing to sort of keep in mind. To produce something which is more homogeneous in space, you put a sieve or a grid. You can, if you smoke, you can just take a sieve and blow through the sieve, and the smoke creates this some turbulent motion. So again, here there is a characteristic scale, which is the distance between those holes. All right. So once you think about, keep that sort of picture for a moment in mind. So we are interested in or the coffee cup. You are mixing the coffee with a spoon of certain characteristic size. All right. So what is the phenomenology of this? Before I go to any further, let's see what one sort of wants to do here and observes. Now, it's a nonlinear equation. Otherwise, that's a nonlinear term here, and you should think about this is a term sort of like an engine, which is doing something, this nonlinear term, and there is a brake by the viscosity, and sort of the relative size of those two effects is an important thing. The ratio of the nonlinearity to the braking, the viscosity, it's called Reynolds number. Now you have to be a little bit careful here. How do you define that? There are some symmetries of this equation. There are obvious scale symmetries. You multiply times and distances by numbers, and then you have to multiply the velocity, which is meters per second, also with similar consistent ratios, and the equation stays invariant. There's another symmetry, which is a Galilean invariance, which means that you can always go to a moving frame with constant velocity. If your fluid is moving everywhere with constant velocity, obviously you shouldn't count that as a high size of the velocity field. So only differences of velocities are important here. You can always go to the moving frame of the constant motion fluid, and then it looks nothing is happening. Okay, so the Reynolds number is a certain ratio of the velocity, size of the nonlinearity here, to the viscosity, but you have to take the velocity difference, and then you have to put some powers of the scale, which is here, in order to make something which is invariant under these symmetries. So that's a definition. You could take the definition in these examples. The velocity difference is just the v here minus the v there, which is 0. So the v in all these cases, and the L is the L here. And then viscosity is viscosity. Maybe more mathematically, you might take something like the Sobolev norm, first Sobolev norm in the region where you are, multiplied by appropriate powers of L. But so think about the Reynolds number in these examples in those terms. Then what you observe is the following. Leave that. All right, so when the Reynolds number is small, less than something order unity, you have a regular flow. Nothing interesting is happening. It's called laminar flow. When you start increasing the Reynolds number, so it means either changing this L or the nu or the delta U or all of them in definite fashion, you get bifurcations, and finally the flow becomes increasingly complicated and finally, in some sense, chaotic. And finally, once the Reynolds number is very large, bigger than 10 to 2, you get a very peculiar chaotic behavior which has the name turbulence. In the limit of very large Reynolds number, 10 to 6, 10 to 7, which is not large if you think about, it's very easy to have 10 to 7 in air, just in regular circumstances already, or in water. When it becomes very large, one observes universality in the sense of the talk of Tom Spencer. Namely, certain things which will come in a moment become independent of the nature of the forcing. Okay, so you can change the details of the forcing, and you observe the same phenomena, same numbers actually. Okay, so what about on the mathematical level? This is a nonlinear, you can view it as, well, it is a nonlinear parabolic partial differential equation, actually an integral partial differential equation because of this relation here. Anyway, it's a nonlinear PDE, and the mathematics, at least during the past 20, 30 years, most of mathematical studies on this equation have really been PDE studies of it. So in that framework, you are interested in proving the existence of solutions and study existence, uniqueness, smoothness of solutions. This goes back to a long time ago already. It was Leray in 33 who proved in 3 dimension global existence of solutions, not uniqueness and not smoothness. They are weak solutions, so distributional solutions of this equation. They are, all you know about them is that they are L2.
It's for Navier-Stokes.
For Navier-Stokes, nu is positive here.
Yeah, it's very important.
It's very important. I will come in a moment what happens when nu goes to 0, but at the moment it's nu is positive, unless otherwise stated. So Leray proved the global existence of weak solutions and uniqueness he couldn't prove, and ever since it has been open. If the Reynolds number defined in whatever way you want to define it here for the initial data is finite, then a smooth solution exists, but for a very short time going to 0, for Reynolds number going to infinity. I mean, it's proven to exist. It's not a claim of whether it really exists. Strong means smooth, yes. Basically, you should think about that uniqueness in this case means smooth. Once you prove that it's unique, then it will become smooth.
The question is, the thickness of solution, does it allow infinite amount value of vorticity? Or just, it's a jump?
In this case, the weak solution, okay, let me say what it says. It says that integral u squared is finite, and integral gradient u squared over space and time is finite. So vorticity can be infinite. Can be infinite, but then the set of space-time points where it's infinite, you get bound for that, and its Hausdorff dimension is not too big.
It's integrable singularity.
Integrable singularity is in the L-square sense of the vorticity, in space and time. In space, you know nothing about the integrability of the vorticity. But okay, well, maybe, okay, you are the chairman, but nevertheless, maybe we could leave for discussion some things, because that's not what I'm intending to talk about at all. There's another approach within the mathematical and, of course, in the physical community, but that was started also in a serious way by a mathematician named Kolmogorov, and that's the statistical theory. And here the idea is that, well, okay, so the main concern, let's go back to that. The main concern here at the moment, or for the past 20 years within the PD people, has been the question whether solutions blow up in 3 dimension. And that has been a difficult question, and the more you look at it, the more it seems to be difficult, at least when you interview the people who are involved. Nevertheless, it's fair to say that it's pretty far from what physicists have been interested in turbulence, this blow-up of solution in 3 dimensions. And the thing which is closer to those concerns and the real turbulence issue is the statistical theory. So what do you want to do here? Well, here you want to focus on typical, not individual solutions. So what do we want to mean by typical? Well, everybody knows from dynamical systems what you want to mean by that. This is a dynamical system, first derivative in time. So what you have a dynamical system in some space of vector fields of your region omega. All right? Well, provided you can prove, of course, existence of solutions. Now, think about it as a dynamical system, then what you would be interested in is an ergodic invariance measure of the dynamical system. If you had such a thing, then you would know that the time averages of suitable observables would be the same things as if you wish, the snapshot averages, the averages over just snapshots of the fluid at given times in the invariant measure. So time average is the same as the average over the invariant measure. This time side doesn't know about time. Now, again, from ordinary finite dimensional dynamical systems, you know what the natural measures is. They are the ones which are stable under a little addition of noise, so the ones which put noise in. So that's an alternative approach to turbulence, and to formulate really a mathematical model and question about that, let me do it now. Ever since from Kolmogorov, people have been thinking about as a model of an idealized turbulence, not the turbulence of an engineer who wants to plan the wing of the plane, but the turbulence of the theoretical physicist and the mathematician who wants to address the question of universality. That model could be stated, for instance, as follows. You take this force here, random, stationary in x and t, so it's translation invariant in x and in time, and you take it in scale L. So you think about your spoon, which you are mixing the coffee, but the size is L, but otherwise you're doing it randomly. And no prejudice as far as where you are in the cup, etc. For instance, you could take a Gaussian, and that's mostly what in the mathematical literature have been studied. Gaussian noise with a certain covariance. Never mind too much about that. Basically, you want the noise to be concentrated on scale L, so the covariance function of the noise in its Fourier transform should be localized near L inverse. Okay, so take such a model. That's a perfectly well-defined stochastic partial differential equation, and you can ask about questions about the solutions of the equation. Now, what do you know mathematically? Of course, again, almost nothing. In 3 dimension, you know that weak statistical solutions exist. Again, parallel to the case of the deterministic problem. Weak solutions exist in 2 dimension. Remember, we had existence and uniqueness of solutions, and here you have existence of invariant measure, but not with assumptions which we are interested in, namely the turbulent assumptions. Although I don't think that should be a difficult problem to actually prove that there is a unique invariant measure. Now, so that's, of course, the basic thing what you would like to do, but the thing you're really interested in is after you have the unique invariant measure. So let's talk a little bit about what one really expects. Okay, this invariant measure is experimentally accessible. You look at time series, you measure the velocity at a given point in various instances of time. You take the time average, or you take photographs of various realizations of the flow at given time. And you can calculate these averages in the invariant measure. These things, either this side or that side. And that people do experimentally all the time. So the upshot sort of those experiments could be perhaps stated in the following fashion. There seems to exist a length scale in addition to the length scale L, which our spoon was doing, eta, let me call it eta, and that scale goes to 0 as the Reynolds number goes to infinity. So if you take the viscosity to 0, that scale becomes microscopic. And what happens is that the invariant measure exhibits scale invariance on those scales. Scale invariance in the same sense as in the lecture of Spencer. So let's look at a couple of examples. The first example goes under the name energy spectrum. So measure just the correlation function, exactly like the spin correlation function which Spencer was dealing with. Velocity at point x and velocity at point y. The stationary homogeneous, so the average of u should be 0, and you look at how they are correlated at different points. So I use this notation that the bracket means the average over the invariant measure, which experimentally is given by either of those formulae. Well, if you are stationary in x, translation invariant, that's a function of x minus y, and you can look at its Fourier transform. And what you observe is the following. This Fourier transform has the following behavior. It has a pure power law, more or less equal to k to power minus 11 over 3.
So this is the Fourier transform of the correlation function.
Exactly. Fourier transform of the correlation function. Has a peculiar power. It's not exactly accurate, this 11 over 3, but seems to be pretty good experimentally, 11 over 3. And this holds in the sense of Spencer, this tilde here. There's a constant which is not universal, etc. But this power seems to be within, well, at least it's believed, and or hoped. And there is this holds when k is between this, k inverse is between this small scale and the large scale.
But the constant is pretty well known.
Experimentally.
2.1 epsilon and 2.
I'm sorry?
Experimentally means physical experiment or computer experiment?
These are physical experiments in 3 dimensions. There are no reliable computer experiments in 3 dimensions. In 2 dimensions there are, but not in 3. All right, so there is an energy density. Velocity squared is the energy, kinetic energy. You are homogeneous in x, so it doesn't depend on x. And we can write it from this formula, putting x to y as an integral over what one calls wave numbers, the absolute value of the Fourier transform variable k. And then you can ask how much energy there is for various scales in the momentum space. Well, that's simple. Just add d minus 1 to that in 3 dimensions. So you see the following sort of behavior. Energy in scale k is proportional to k to the power minus 5/3. And it goes very quickly to 0 as k becomes very large when you are in the ultraviolet. So you expect that the energy stays finite even as the viscosity goes to 0. This integral is convergent at large k, if that's the correct behavior. When viscosity goes to 0, eta goes to 0, so you don't have any decay there, but this is enough. Whereas the gradient of u seems to diverge, because gradient has an extra k squared, and so you get the positive power of k, and it certainly doesn't seem to converge as viscosity goes to 0. So that's one consequence of these experimental observations. Now, there's more to it. There's a whole picture now about what the nature of the stationary state is. After all, the energy is conserved if you don't have the friction. That's the Euler equation. So there is certain reflection of that in our stationary state. And you can write an equation, what happens to the energy if you are a stationary state. You write an Navier-Stokes equation, and you get that 0 is a sum of 2 terms. Nonlinearity doesn't count at all, and you have something which is proportional to the viscosity, which you call the energy dissipation, and something which is proportional to the force, which is energy pumping. And if that's 0, those two balance each other, and that's something which, well, it's called the energy balance. And again, if we believe in these powers here, if you look at the dissipation of energy, then it seems to be taking place mostly close to the small scale eta, k squared, k to positive power. So this is dominated by something happening in the small scales. And the pumping of energy, because I put the force in the large scales, happens there. So you have the picture that you put energy in the spoon size, then it sort of just flows without anything happening to it in scales, creates smaller and smaller motions in scale, and finally gets killed by the dissipation in this very small scale if the Reynolds number is large. So that's a sort of a picture which you infer from these experimental observations and this simple equation which the stationary state should satisfy if it existed. So this is the cascade picture of Richardson-Kolmogorov. Constant flux of energy in momentum space from injection scale to dissipation scale. That's the official picture of turbulence, or what at least one would like to perhaps, well, if forced to bet to be true. All right, so what does it mean? Let's look at it a little bit more, what it means. In particular, this thing is fixed. It's just the amount of energy you put in. I'm not doing anything. I'm just keeping the spoon. I'm changing the viscosity, changing it from water to something, alcohol or whatever. And I'm pumping the same energy. So it has to stay the same as this. So what has to happen is that this limit is non-zero, because it's just given by the pumping. So in particular, well, as we observed already before, the gradient u squared has to become infinite in the limit of viscosity goes to zero. People usually call that dissipative anomaly. This goes to infinity, this goes to zero, and together they leave some trace. How we should interpret that mathematically? We should interpret it perhaps in the following way. As you take viscosity to zero, the stationary measure of the Navier-Stokes equation should be concentrated. Well, when viscosity goes to zero, you get the so-called Euler equation. It should be concentrated on dissipative weak solutions of Euler equation. Euler equation naively conserves energy. There is no friction. But what you get once you take the Reynolds number to infinity, you should get some invariant measure of the Euler equation sitting on dissipative weak solutions of it. Now there's various things which you can do with this 1/3. Heuristically, it's very, very easy to see that you should expect the velocity to be more or less Hölder continuous with exponent 1/3. And indeed, it's a theorem. Well, in certain cases, in 2 dimensions, that it can't be more than that, but let's leave it like at that. The expectation is that the velocity is a little bit rough, Hölder continuous, not differentiable. In 2 dimension, let me say a couple of words. When did I exactly start, by the way? Any idea? 20 past, or what was it? Okay. In 2 dimension, there is a little bit different picture. Now the observation is that the energy spectrum goes like k to power -3 and not -5/2. So various things change here. First of all, the energy, this integral is negligible around the ultraviolet here. Not this one, but where is it? The energy. It converges very well at k going to infinity, k -3. So there's no dissipation of energy at scale, at the short scales. So energy doesn't do at all the same thing as in 3 dimension. However, in 2 dimension, there is another conserved quantity of the Euler equation. In addition to energy, there is so-called entropy, which is basically just related to gradient of u squared, actually the rotation of u, which is called vorticity of the velocity field. That thing is conserved by the Euler flow, and you can do exactly the same story as was done here. There is an entropy balance. Entropy is dissipated and created, and you can do the same calculations as was done in energy, and you get the picture that the entropy now is now dissipating at scale, short scales. The gradient of the U is doing that. There's, again, cascade of entropy. It's called the direct cascade in the jargon of turbulence. So entropy is going in. You put in this conserved quantity. It goes, doesn't change until it reaches the dissipative scale, and then it gets dissipated. Well, what happens to energy? Well, what happens experimentally now is that there is another range. And these experiments are, this is numeric, this is real experiment, very accurately k to minus 3. And this is a completely reliable numerical experiment. You can do this in computer in 2 dimension. Again, very accurately minus 5/3. Both are quite recent, last year actually. There is an inverse cascade of energy. Well, if you look at this, now the energy, the integral diverges at small k, right? If I integrate this over k, one-dimensional k, it blows up at k equals 0, which means in x-space large distances. So now the energy wants to go to the large distances. There's nothing, if there is nothing to dissipate it there in the large distances, then it just keeps on growing. And what you expect actually in such a case is that there is no stationary state for the velocity, only for the gradients of velocity. One is very familiar with such situations in statistical mechanics, for instance, quantum fields in 2 dimension. Again. But if you have boundaries in the, if you, for instance, have a finite volume, if you are on a torus and you have a constant velocities present in the system, then the energy can go to those constant velocities and increase linearly in time. Okay, so that's the experimental sort of abstraction of what people have, of course, been doing experimentally long time, but nowadays, at least in 2 dimension, this is in pretty good control. There's another thing in the scale invariance, very striking and very important, and let me spend 1 minute on that. It's the phenomenon of so-called intermittency. One expects not only this scaling of the 2-point function, but a whole range of scaling exponents, Hölder exponents, a spectrum of Hölder exponents, actually. You look at something, if you were to look at Hölder continuity, you look at u at x and u at 0, and that's a vector, so take it parallel to the distance, the vector from x to 0, and look at moments of this random variable for various x's. They seem to scale again when x is between those 2 scales with certain powers. And all these powers seem to be non-trivial, not multiples of each other, like the so-called Kolmogorov theory from 60 years ago predicted. They are pretty good approximation for small n. They are given by n over 3, but not exactly. And they seem to be all different, a concave function, not a linear function of n. This phenomenon is called multiscaling or intermittency. I'm not going to explain the name of what it means, this word, but our definition be just that there are this whole spectrum of Hölder exponents. It seems that you are not dealing with a function which is Hölder continuous with high probability of certain degree, but it has a whole spectrum of Hölder continuity properties. In 2 dimension, again, some very striking difference. For short distances, it seems to be okay. I mean, differentiable in some sense. Whereas for large distances, the same as in 3 dimension, like in Kolmogorov theory, but exact. Even the up to log, what I put here, doesn't seem to be there experimentally. Okay, that finishes the introduction. Okay, so what I want to say is let me repeat the main expectations we have on Navier-Stokes: the cascade picture of energy, the dissipative anomaly, the measure sitting on weak dissipative solutions of Euler equation as Reynolds number goes to infinity, and this intermittency. Yes, it's very important they will be non-unique. It's important they are non-unique, actually. The whole ensemble of solutions contributes. Now what I want to describe is that there is a model where all these things actually happen, and not so unrelated to Navier-Stokes. Cascade picture, dissipative anomaly, and intermittency. And measure sitting at weak solutions, a whole ensemble of them. Well, the motivation of this model is the following. Look at turbulence again, and let's look at this vorticity, which I mentioned already. That's the curl of the velocity. In 2 dimensions, it's just this combination here. It's advected by u. What do I mean by advected? Well, you just plug in the Navier-Stokes equation for that, and it satisfies these 2 equations depending on the dimension. That's the commutator of the vector fields. As you see, if you didn't have any viscosity or forcing, then what happens is that you are just transporting the omega. It's a scalar or pseudoscalar in 2 dimensions, and it's just transported like a scalar by a diffeomorphism. In 3 dimensions, it's a vector, and again, it's translated like a vector by a diffeomorphism. So U generates a time-dependent set of diffeomorphisms, and those omega is just transported by those. Now, it's a natural question now to study what happens in general if you have somebody gives you a turbulent velocity. How does it tend to transport scalars, vectors, things like that? To study such equations where U and omega are not directly related, like here. That, of course, from the point of view of applications, that has huge importance if you think about, say, pollution in groundwater due to toxic waste flowing. You want to study. That's a particular case of advection of a passive scalar, namely the equation we are studying. Okay, so just a couple of words about what is here. So let's look at, instead of the Navier-Stokes equation, we have omega here. Let me put, instead of omega, a scalar, and look at an equation where I have just linear equation for t, but I have a u here, which I will, in a moment, specify what I want it to be. So there is diffusion, there is transport, there is a source. Now, if I have no diffusion and no source, then t is just transported. That's undergraduate PD, right? T at time t and point x is just what it used to be on the trajectory which reaches from time s to time x. It's just what it used to be here. That's called the method of characteristics, right? That's simple enough. So that's a transportation. If you add a little bit of diffusion to it, not much changes. Instead of looking at the differential equation, you look at stochastic differential equation. You add a little Brownian motion. So you have the same equation, but your velocity gets a little Brownian addition. So instead of having a deterministic unique trajectory, like in the case of smooth vector fields, you have a fuzzy trajectory. Instead of having a single solution, you have an ensemble of solutions. You have a Markov process in RD. Okay? That Markov process has a transition probability, of course, nothing else than the heat kernel of the operator, which is here. And t at time t is given by, well, just by integrating with the transition probability kernel of the Markov process of t at time s. Pretty undergraduate too. Now, what about, well, once you add the source, again, ordinary linear differential equations, not only you transport from time s to time t, but you also create all the time during your trajectory more t. Okay, now let me now tell you what we want to do. We would like to ask, how does a typical turbulent velocity transport this t? Well, we don't know what is a typical turbulent velocity, so let's make the question a little bit simpler, and it turns out that it's still complicated and actually has interesting consequences. So I will take the typical, I will take a Gaussian velocity. I take a stationary Gaussian random field, which is Helder continuous in x, like I expect in turbulence, with some exponent. Helder continuous with some exponent. In turbulence, it has a certain value, which we expect. Here I just take it as a parameter, and white noise in t. So every time step, you sort of change it, the velocity. And what happens now is the following. Then you put, again, a source, like the spoon in the coffee cup, in scale L. You put it white in t. So this is an equation like our Navier-Stokes, except that t is not u, but t is just something else. And you want to study, again, the invariant measure for t and its properties. Now what happens is a little bit striking. When the diffusivity is non-zero, we have these fuzzy trajectories. We have the Markov process. If I had a smooth vector field, then obviously, as I take the diffusivity to zero, I would regain a deterministic trajectory. So the Markov transition probability would become a delta function on the trajectory. Well, we are in turbulence not interested in smooth vector fields, but Helder continuous ones. And what happens is actually, so in particular it's not Lipschitz and you don't have uniqueness of solutions necessarily. What happens actually is that once you, for a turbulent U, take this limit of kappa going to zero, you don't regain determinism. You still retain a Markov process. You still have a full diffusion process. That's the theorem.
The vector fields you get in the limit are held, and so you have a Euclidean solution.
Yeah, I mean, you know that x dot is square root of x, doesn't have unique solution, right? That has many of them. If I take this stationary Helder thing, it actually has a full set of solutions, and naturally what you get is a Markov process. The solution of the ordinary differential equation, which you can't really show that it has unique solution, actually is a measure. There's a diffusion process. The solution is a diffusion process. So turbulence is inherently non-deterministic in that sense. Trajectories diffuse. Identical initial conditions don't have identical consequences, like in chaos. In chaos, they have identical initial conditions have identical consequences, but you have exponential separation of trajectories. Here it's not the case. Here they have identical initial conditions, have different consequences, and nearby ones diffuse. This is because the vector field is not smooth, but it doesn't imply, the smoothness doesn't imply that you have non-smoothness, doesn't necessarily imply that you have a diffusion process. That happens, but that is by no means completely obvious.
Maybe not precisely diffusion, it's some random process.
It is actually super diffusion.
Yeah.
But it's more or less like diffusion. Okay, consequences. Well, if the trajectory is diffuse and you're transporting something, then it's sort of obvious that the something is going to diffuse too. And what you get actually is that the energy, which I could call energy, it's not physical energy here, but it's the L2 norm, well, just the t squared, which is formally conserved by the Euler limit, the kappa going to zero. It's formally conserved, not so in the rough U. What happens is that you again get this energy balance in the stationary state. You get the cascade. So the dissipation will not go to zero as kappa goes to zero. Just like what I was telling you in Navier-Stokes, exactly that thing happens here. Energy is dissipated at small scales. It cascades there. There is a dissipative anomaly. And more importantly, the limit measure as kappa goes to 0, is supported on weak dissipative solutions of the corresponding equation. That's like the Euler equation. Formally, it seems to converge t squared, but in reality, it doesn't in this limit. So that part of Navier-Stokes expectations actually happens here. But not only that, also the part of intermittency happens here. It so turns out that the invariant measure for t, let's finally put the constants here also, has the following property. You look at, again, the differences. So you try to measure how Hölder continuous the t is. So what you get is that there is some non-universal number. When you look at the nth moment of differences of t, there's a non-universal number. There are universal exponents here, which don't depend on the details of the noise, and then corrections depending on the dissipative scale and the L. Okay, and they are not linear. You have infinitely many different exponents, and the way you well, I have no time to go at all how one gets all these things, but what happens is that sort of the rough velocity fielding induces correlations. What is if you are looking at t to power n? You're looking at motion of n fluid particles. Okay, so you have this n diffusing particles, and they're diffusing in the same v with this particular u, which is statistically inducing correlations to those guys, and this will be actually more or less bound state energies in the motion of n fluid particles. So what are the lessons for turbulence from this model? Well, it shows that, I mean, we didn't, of course, solve turbulence at all. We didn't even put a turbulent velocity. We put in a velocity which is rough, like we expect turbulent velocities to be, and we asked what are the consequences for transport. Turbulence is one example of transport, but not at all as simple as this one. Nevertheless, even when we put just a scale invariant velocity in, we get the following thing. We get these fuzzy trajectories, the energy dissipation at zero diffusion limit. We get these dissipative weak solutions, which are important as Reynolds number goes to infinity. And in this particular case, we even see that even if we put a non-intermittent u, so u which doesn't have the spectrum of Hölder exponents, we are going to generate this Hölder exponent due to certain correlations in the motion in this rough velocity. So I think these models sort of, if there is any, the interest what is in them is that they are sort of close to the Navier-Stokes equation in certain senses. We can make the similar expectations as in Navier-Stokes, but you can also prove them here. What are the prospects? I think I should finish. Well, first of all, prospects as far as what could one try to do from the mathematical point of view. Of course, these passive advection problems are by no means completely understood everything yet. What I explained to you was the advection of the scalar in the simplest situation. One should certainly look more into those, but one should also maybe, in the case of Navier-Stokes rather, to study dissipative weak solutions of Euler equation. People have been doing that, especially Schneermann has been doing interesting work on that. And recently also there was a nice paper by Duchon and Robert studying the dissipative anomaly, which we expect to be there in the weak solutions of Euler equation. Now, as far as mathematics is concerned, I think the most accessible question, and that's by no means without physical interest, is two-dimensional turbulence. Well, one thing what one could try to do is to study the inverse and direct cascade deterministically. So you put in some initial condition and you ask what happens This was done in other equations, Schrödinger equation by Bourgain and Kuxin. At least they had some results to those directions. It might be interesting to look at it in 2D Navier-Stokes in the inverse cascade. Existence and uniqueness of a stationary state should be a problem of statistical mechanics, so perfect for mathematical physicists. And the more challenging problem to prove the absence of intermittency. As I told you, there is very reliable experiment in real system, real, not computer, not virtual, but real, in the case of direct cascade, the ultraviolet, and computer experiment in the case of the inverse cascade. Both very accurately, well, within the accuracy, but seem to indicate that there is no anomalous scaling. All these exponents are like Kolmogorov-Krishnan predictions are. And if that's the case, then maybe that could be accessible to mathematical approaches too. So that's certainly a challenge, and not clear that one can really do it. Another full set of questions go under the name of weak turbulence, as pioneered by our chairman. And again, it seems to me that mathematical physicists might have some chance of making a contribution there, because there, in contrast to Navier-Stokes, you really seem to have a perturbative problem in some sense at least. So one could perhaps, well, I think one should attract a little bit attention on going into trying to do mathematical work also there. Okay, I think it's time to stop.